Hello, everybody. It is me again, coming to you from smoky Fort Collins, Colorado. I live in Fort Collins. So let's go ahead and take a first stab into the material. I'm excited I get to use this stylus, and they're written on a screen before. So I'll be learning as I go. So this is some optional reading. Remember that the textbooks are optional. And here is a helpful picture of what these different books are. So I'm just taking the first initials of each author when I refer to these books. For what it's worth, I think these two books in particular are very useful. And like I mentioned in the previous video, this course was informed really by these three and another book. Software for this course, we have, of course, R and RStudio. You know, R has recently gone to 4.0, and I strongly recommend that you upgrade your R if you have not yet to R 4.0 or higher. They changed a few things, but there is one important change about how they consider variables with text. And so for my code to work on your computer, I hopefully will always test my code on my computer. And so for your code to work on your computer, I recommend that you upgrade to R 4.0 or higher. RStudio, the latest version available, should do the trick. RStudio is, of course, the GUI, which I'm sure some of you know. Stands for Graphical User Interface to R. You really have to install these together, and RStudio is the one that you'll be using. So I always, in teaching these introduction to statistical topic classes, the first class is always hard because it's like an introduction to the introduction. And I always never know how to get started. So here I go. Spatial data analysis. You know, it makes sense then to start with a few historical facts, correct? So I think a good definition of spatial statistics, concepts and methods, and I have to click draw. All right, learning. Concepts and methods to analyze data collected over many geographic locations and possibly many time points. So here is our first caveat. Most often when you're out there collecting data, it is very rare that you decide to collect data across space, across many geographic locations, but only one time. Most commonly, it is both spatial and over time. But the methods to analyze space-time data are more complex than space alone. And so in this class, we will be dealing with things that are spatial. But after this class, I think you won't be too far away if you have to analyze data that is spatio-temporal in nature. So in reality, you mostly have space and time, very frequently have space and time. But in our class, where spatial statistics, at least this time around, we're going to be focusing on spatial. So I went back and looked at other people who have been talking about spatial analysis, spatial data, and spatial correlation. So the first thing that pops to mind is Mr. Tobler. I always like to say that if you're the first person to say something, what you say can be pretty simple. So Waldo R. Tobler, this cat right here, he said the first law of geography, 1970, not too long ago. He said everything is related to everything else, but near things are more related than far things. When you're the first to say something, you can get away with having that be the first law of geography. But what Tobler is saying is distance affects how related things are. How related things are, another word for that is correlation. So we'll be thinking about distances a lot. We'll be thinking about how far apart our observations are, because we're thinking back to this first law of geography. Sir Ronald Aylmer Fisher, who is frequently thought of as the father of statistics and absolutely not a nice person. Dr. Fisher, Professor Fisher, he's British. Professor Fisher had terrible eyesight and was terrible, actually a really not a nice person. But as the father of statistics, it wouldn't surprise us that he had some things to say about spatial correlation. So in 1935, he noticed that patches of wheat in close proximity are commonly more alike as judged by their yield of crops than those which are far apart. So maybe he really was the first one to think of this first law of geography. Of course, this was 35 years before Tobler. And then those of you who have had me for introductory statistics courses may recognize this as a bonus for exams, for a particular exam, in fact. And William Seeley Gossett, who was a chemist for Guinness, for the Guinness Brewery in Dublin. If you ever find yourself in Dublin when we're allowed to travel again, there's a plaque for the t-test, the famous t-test. So William Seeley Gossett, also known as Student, he wrote in 1910 to Carl Pearson that he noticed correlation weakens. Correlation weakens. Correlation measures how alike things are. Correlation weakens as the unit of time or space, remember what I said about time and space, grows larger. And it would be a great thing to work out the law to which correlation is likely to weaken. So what he is describing, what William, Dr. Gossett is describing, is actually a correlation functions. And I wonder if I can get that in with my stylus. Let's try. Correlation functions. What Gossett is talking about, he notices that correlation decays, correlation weakens. And it doesn't do so randomly, it does so systematically. And he thought that there would be a law, some kind of a law, and think law in mathematical terms, and old-timey mathematical terms at that, right? We're talking 1910. So he is describing a correlation function. He's not calling it that, but in the future, we'll be talking about spatial correlation functions, and I think Dr. Gossett would be proud of us. So what about me? My personal definition, and again, select. My personal definition of spatial correlation is rather heuristic, but I say similar data at similar locations. So you're talking about high among high and low among low. That is my personal definition of spatial correlation. We're looking for high values that are located near other high values and low values that are located near low values together. So the question is, okay, what does similar mean? Can we quantify similarity? Well, similarity in data, when you're a statistician, is measured by positive correlation or covariance. And I just want to note that correlation is covariance over the first standard deviation times the second standard deviation. So basically the sign of the correlation is the same as the sign of the covariance, right? If this is a negative number, this is a negative number. If this is a positive number, this is a positive number. And so really when we're talking about the correlation, it is really a scaled covariance because the product of two standard deviations must be greater than 0. And so you can see that the correlation is simply a scaled covariance. The signs will remain the same. What about similarity of location? All right, well, similarity of location can be measured with distances. So I'm getting kind of formal here. I'm calling it a distance metric. There's actually several kinds of distance metrics. Some of you may have heard of Euclidean distances, but that's only one of many distance metrics. Another one would be your, sometimes are called taxicab distances. So a Euclidean distance, since we're talking, a Euclidean distance looks like that, whereas they call it the taxicab distance or the Manhattan distance. As an example, I'll use red. The Manhattan distance would be this, because if you had a building here, you would have to go around the block, right, to get from this point to this point. So the Euclidean distance is, as they say, as the crow flies, very straight line. And something like the Manhattan distance, I've seen it called the taxicab distance, would be more like the red line because you have to go around the block. Believe it or not, these things are generalized, and there is something called the Minkowski distance. That generalizes Euclidean, Manhattan distances even further. The Euclidean distance, the black line, is by far the most common distance metric. The other one, however, we can measure similarity in location also using adjacency. Adjacency requires that we don't need to know how far apart things are. We only need to know that they are near or directly near each other, in that they're touching. They share a border, or even more formally, sometimes it's one or two vertices. Oh, I kind of like this. They're sharing a border or one or two vertices. So depending on the type of data we're dealing with, how we measure similarity in location will be different. We'll be either using a distance metric or this concept of adjacency, or basically are our regions touching? Okay. What I like about spatial analysis, and specifically our concept of spatial correlation and spatial prediction, is that they can be quite intuitive. So I mentioned that, this weekend in Fort Collins, the air quality was very bad. There's a few wildfires. I think there's a wildfire around here. There's a wildfire. And then there's also around here a wildfire. That's not necessarily the directions that they're going, but the wildfires are occurring somewhere here and here. Amongst others, I know there's one over here as well. So when I go outside, I like to look up the air quality index, and here's what I saw. So Fort Collins is real bad, 162, that is classified as unhealthy. Boulder was better, Greeley was better. Denver is somewhere in that generally somewhat unhealthy range. But what about Loveland? So that's star number one. What would our prediction be about Loveland? Loveland is a wonderful town. Can we predict air quality for Loveland? Well, I hope as I'm asking this question, you're thinking, well, it's between Fort Collins and whatever this is. I forget what this town is called. Why would it be that different than 162 or 153? Greeley is a little bit farther away, but maybe we include Greeley into sort of the zone of influence. And so intuitively, I hope you're thinking, well, it's like an average. It's like some kind of an average. And probably if we take something like an average of the Fort Collins reading, this reading, and maybe the Greeley reading, maybe even the Boulder reading, if we take the average of these 4 readings, you will get a sense, you will get a prediction for Loveland. So I don't know, something like the average of, this is for Loveland, the average of 162, 153, maybe 74, maybe 80. And I'm saying question marks here because you would recognize that Loveland is far closer to Fort Collins and this reading of 153 than it is to Boulder and to Greeley. Okay, so you're almost a spatial statistician now. That sounds good. What about the other star? What about just outside of Fort Morgan in star number 2? What would our prediction be out there? Well, there's not any immediately near readings for us to come up with a precise prediction. We might just go ahead and say, I don't know, how much influence do these have? Maybe air quality decays. Oh, sorry about that. Just pressing stuff now. Maybe air quality decays just over here, you know, just along I-25. All right, this is I-25 right here. But then, you know, once we get out past Greeley, maybe there's not much of the bad air left, or maybe it just kind of decays to the average bad. You know, 74 is not great air quality. It's still moderately unhealthy. So maybe for outside of Fort Morgan, maybe it's just the global average now. Because you're far enough from your observed data points, whatever metric you want to use, Euclidean, Manhattan, Minkowski, you're far enough from your observed readings that, yeah, maybe you shouldn't get influenced that much by these 162 and 153 real bad air quality readings. Okay, so hopefully that made sense. So then the question is, where should we be more confident in our prediction? And I hope that intuitively, you would agree that you would be more confident in Loveland than outside of Fort Morgan. Because you are more near to your observed values. Because you're more near to observed values, there's less of a reason to think that you're wrong about your prediction in Loveland. Who knows what's happening in Fort Morgan? That's not to say that a global average is a bad prediction. If we weren't in spatial statistics, the global average would be a pretty good prediction for an unobserved data point, actually. But because we're in spatial statistics, you want to say, how close am I to other observed readings? And can I use those observed readings to help me make a better prediction than simply the global average? So that kind of concludes my spiel about just very beginning to think about spatial prediction. Now let's think about spatial correlation. If I go back to my personal slide, my personal definition, we're looking for similar data at similar locations. Okay, we're looking for similar data at similar locations. So for here, this is a figure out of a paper, and I don't have the legend up, which is bad form, but it's not necessary right now. The legend is not needed. Blue is a negative number, and more blue means more negative. Green is about 0, and red is a positive number. More red, more positive. All right, so looking at these 3 panels, what is the global average, approximately, for the images above. So you're looking at blue is negative, green is 0, red is positive. Well, as I'm stepping back, there's about the same number of reds and blues in every picture. There's about the same number of reds and blues in 1, and in 2, and in 3. So approximately the global average is actually 0. 0. When you add stuff together, right? What's the average? Right? X bar are my mean. It's the sum of my observations over n. We know n is strictly positive. Well, if you have data, n is greater than 0. And so your average just depends on the sum of your observations. If you sum your observations in each one of these panels, you're going to get about 0. Okay, so then if the average for each one of these panels is the same, what is different? Well, if we rearrange the position, of red and blue dots, of red and blue tiles, we can change the strength of spatial correlation. So intuitively, you're looking here, similar data at similar locations. Reds among reds, right? Reds among reds. Blues among blues. Call it oranges among oranges. Greens among greens. So this has the strongest spatial correlation. Remember, the average is the same. The number of red and blue tiles is approximately the same. But we rearranged such that the red tiles are near each other and the blue tiles are near each other. So this number 3 has the strongest spatial correlation. Well, you might imagine that the weakest spatial correlation, probably you can tell, is over here. 1 has the weakest spatial correlation. When we spot a red tile, sometimes there's a yellow tile next to it. Sometimes there's a blue tile next to it. Sometimes blue tiles touch other blue tiles. Sometimes blue tiles touch red tiles. So 1, in fact, was generated. These data were all synthetic, such that there was no spatial correlation present. And number 2 is in between. Okay, so this slide is really to develop some intuition around spatial correlation and spatial prediction. Moving on. The last thing I want to do today, just to get us started. So I guess I'm really affected by current events. I'm affected by things that are happening right now. And man, the air was bad. On this day, the air was bad in Fort Collins, where I live. So I went to AccuWeather and I said, all right, well, how is the air quality around my city? How is the air quality there? You know, there's mountains right next to Fort Collins. You know, Laramie's right over here. It's Market. It's Market. That's where our university is. Laramie's right over here. Okay. So using maps, if you think of this map that they spatially interpolated, but it's essentially this data, but it's essentially the data I present here. They used some kind of spatial interpolation model that they didn't describe. Why would they? And they came up with this prediction. The more brown the color, the worse the air. So let's practice thinking about patterns, spatial patterns. You look at this map and you're thinking of exploratory data analysis. How would you approach building a statistical model? How would you begin thinking about what to put in for a statistical model that helps predict air quality in this relatively small region? The variables would differ if you were trying to do this across the US, let alone across the world. Well, number one, distance from known sources of pollution. You're thinking, all right, I'm looking at air quality. Can I figure out where the sources of pollution are? Well, yes, I can probably map the two kind of major wildfires in this area. So there's one here, and on the day there was probably one around here. But you can see that actually doesn't help you explain this particular pattern of air pollution, because right near the fires, it's actually better air quality than down in the valleys. So if you are knowing the known, if you do map the known sources, you can't just use a distance. That doesn't help you here. You would be then saying that somewhere over here would be like the worst air. That's not the case. There's something else happening. Well, okay. What about important spatial covariance? All right. We know in this state, in Wyoming and Colorado, we know that elevation is huge. And if you think about, sketching the elevation contours, it will help you in northern Colorado a little bit. But Estes Park is in Rocky Mountain National Park. And the air around Estes Park is worse than the air here just west of Fort Collins. So elevation alone can't help you either. Maybe you include both of these together with like a wind direction of some sort. Now, can you measure it? But I'm trying to show you how I would approach, and maybe how you would approach looking at this map as exploratory data analysis. I would like to demonstrate how I would pick out the patterns in the data to think about building a statistical model. I'm not sure that elevation alone or distance from known wildfires helps us that much here. Then you're asking the question, all right, well, I'm allowed to use the coordinates themselves as covariates. All right, so we can use the coordinates as covariates. So put in a quantitative covariate for longitude, the x direction. Put in a quantitative covariate for latitude, the y direction. I'll give you a lot more on coordinates later. Could I explain some of the patterns by including sort of x and y in the model? So something like x plus y plus x times y. That's an interaction term, right? If you're following along. Probably. The air seems pretty good in the northwest, pretty bad in the southwest, pretty bad in the northeast, and I don't know, average in the southeast. I think this might be a pretty good strategy for this particular picture. But that is really broad brush strokes. This is large scale variation. I'm sure there'll be something left over. There will be errors. There'll be residuals that will be left over that will look a lot more like this than like this. When we are building a statistical model and we're looking at our prediction errors, we're looking at our residuals, we're looking at our errors, we want to be left with something that is looking more like this left-hand panel that is spatially independent than something that is looking like these two panels where there is something spatial left over. So while this might be a pretty good starting strategy, just include the coordinates as your covariates, maybe including the other like elevation and distance from known wildfires. I bet there would be some small scale variation that is left over that might look like this middle panel. And that is where spatial models come in. That is one example of where spatial models come in. This is geostatistical models. Go here. Okay? It's the first day of class. I hope I gave you just the beginning of where we're headed. We looked at some patterns. We'll pick this back up for Thursday's class. Talk a lot more about types of spatial data and start to look at maps. So thank you so much for your attention, and I will see you guys later.